Let's add some properties to our quadrilateral properties summary. We're going to look specifically at rhombus properties today. So again, the handout that you want at the top says quadrilateral properties summary. And on this, we've already summarized all of our parallelogram properties. Here they are, lots of parallelogram properties. And then yesterday, we wrote in our rectangle definition, our one rectangle property here. In a rectangle, you get congruent diagonals. That's something that you get to prove in your homework assignment. There are two more things that I would like you to prove in your homework, and that involves the next quadrilateral. So if you turn the handout over, at the very top, we have the definition of a rhombus. So a rhombus is a quadrilateral with four congruent sides. So I'm going to write it as quad for quadrilateral with four congruent sides. So in order to mark that in the picture, I will just mark that all four sides are congruent. I'll put one tick mark on each of the four sides. A rhombus then has two unique properties that I would like you to recognize and I would like you to prove. So the first property, if you have a rhombus, the diags bisect the opposite angles. This does not happen in a parallelogram. This does not happen in a rectangle. This first happens in a rhombus. So the diagonals, I will write that as diags. They bisect the opposite angles. So I'm going to mark my quadrilateral as a rhombus by putting the tick marks on the four sides, one tick mark on each side. I'm going to draw in then one of the diagonals. So I'll draw in the diagonal that goes from the lower left to the upper right. And what I want you to see is that that diagonal actually takes the angles in the corners and breaks them into two congruent pieces. So these two angles here at the lower left-hand corner are congruent, and so are the two angles at the upper right-hand corner. They are congruent to each other also. That's what we mean by a diagonal bisecting the opposite angles. The other rhombus property also involves the diagonals. The diagonals are actually perpendicular. So a rhombus gives you perpendicular diagonals, and I will write that as perpendicular symbol and then diags, perpendicular diags. So again, if we have a rhombus, I will mark all of the sides with one tick mark. Then if we draw in both of the diagonals, if we draw in both of the diagonals, this property lets me mark a right angle where the diagonals meet. Again, this does not happen in a parallelogram. This does not happen in a rectangle. We first see this property in a rhombus. So the three properties that I'm going to ask you to prove in part of your homework then involve the rectangle property that we have not proven yet. In a rectangle, you have congruent diags. Then, over here, we have two rhombus properties. In a rhombus, you have diagonals that bisect the opposite angles. And in a rhombus, you also have perpendicular diagonals. Those properties also have to be proven. So the next thing that I'd like you to do, let's go to the class examples that we were working on yesterday. There are three that remain. One of them involves a rectangle and two of them involve rhombi. And although one of them is pretty basic, the other two questions involve some algebra that I would like to review with you now, and then we'll practice a little bit more tomorrow. So the next handout that I would like you to get, at the top, this is the one that we were working on yesterday. It says class examples, rectangles, and rhombi. Class examples, rectangles, and rhombi. We did example 1 yesterday on the front, and I believe that we did example 5 also on the back yesterday. So I'd like to look at examples 2, 3, and 4. So in example number 2, here we go. This is a rhombus, so it isn't marked as a rhombus. I told you that it was a rhombus in the directions. So understand, I would like to find all of these numbered angles. Now, angle 3 is really easy to find because a rhombus, notice if I mark it as a rhombus, understand a rhombus is also a parallelogram. It's just a special kind of parallelogram. The opposite sides are congruent in a rhombus. That makes it a parallelogram also. It inherits all of the parallelogram properties. So the opposite angles are also congruent in a rhombus, just like in a parallelogram. So it's quite easy to find the measure of angle 3. It's automatically 55. So we're done with that one. I'll write it in. So what we have to find are the measures of angles 1 and 2, and it's easiest to start by looking at maybe the big angle at Z. There are 2 ways to do this question. So if you ignore the 2 smaller angles at Z, notice the big angle at Z has to be supplementary with the 55. So remember, this is still a parallelogram, so the same side interior angles are supplementary. If this angle is 55, then the big angle at angle Z is 125. So those 2 angles would add up to 180. Now what we have to do is use that to try and figure out then what the measures of angles 1 and 2 are, and we can use one of the rhombus properties that we just described. In a rhombus, this diagonal is going to bisect this angle here. So I know that angles 1 and 2 are the same, and all I need to do is take the 125 and split it in half. So half of 125 is 62.5, and we're done. So that's both the measure of angle 1 and the measure of angle 2. Those are both 62.5. Now, I suppose there's another way to do this. There's another way to approach this. Understand the triangle WXZ. If you look at that triangle by itself, it is an isosceles triangle. Because this is a rhombus, there are 2 sides that are congruent. So I know that this angle at 1, it also has to match this angle here. I know these have to be the same. I've got an isosceles triangle. I suppose I could turn it on its side. There we go. So if this is the 55 at the vertex angle, if I take 180 and subtract the 55, that again gives me 125. So I need to divide that into 2 equal parts. That would give me 62.5 and 62.5. So that's another way to get the 62.5. You can use the isosceles triangle. Very good. Let's take a look then at example 3. So in example 3, again, it's still a rhombus. So all of these sides are the same, and I would like to find the lengths of the sides. Now, once I know one of the sides, I know all of the sides. They have to be the same. So, but notice I've got 2 variables going on here, so we're going to have to reach back and use some of your algebra skills from Algebra 1 in order to solve this. So let's write the 2 equations that we know are true. So I know that the right side and the left side in this figure are the same. So I know the j plus 1. That has to equal the k minus 3. I also know that the 4k minus 6j, that needs to equal the 2j minus 4. So I know the top and the bottom sides are the same. Now notice I have 2 equations and I have 2 variables. So what I'm going to do is organize all of the variables on one side, on the left side of the equation, and I'm going to put all the numbers on the right sides of the equation. So the first equation is j plus 1 equals k minus 3. So I'm going to move the k to the left side. That'll give me j minus k. And I'm going to take this positive 1 and move it to the right side. That's going to make a negative 1 combined with the negative 3. That makes a negative 4. So I have taken the first equation and I have rewritten it so the variables are on the left and the number, the constant, is on the right. And I'm going to do the same thing here. So I'm going to do a little rearranging here. This 2j is on the right. If I subtract 2j from both sides, that's going to give me a negative 8j on the left. The negative 6j minus 2j is going to give me negative 8j on the left. So I have a positive 4k still on the left, so I'm going to write that as plus 4k. And I changed the order there because I want the j's to be above and below one another, and the same thing with the k's. So then finally, on the right side here, again, what I have left is a negative 4. So when I look at these two equations, I would like to use a method called elimination. So to use elimination, I would like to get the coefficients on one of my variables, either on the j or on the k. I would like these coefficients to be opposites. So right now, I have a 1j minus a 1k equals a negative 4, and a negative 8j plus a 4k equals negative 4. What I'm going to do is take the top equation and I'm going to multiply everything by 4. This is not the only way to do this, but this is one way to do this. That's going to make a negative 4k here, and that's going to cancel out with the positive 4k and allow me to solve my system of equations. So let's rewrite this carefully. If I take both sides of that top equation and multiply by 4, that's going to give me a 4j minus a 4k equals negative 16. And the bottom equation, I don't want to do anything to it. I'm going to leave it as negative 8j plus 4k equals negative 4. And now what's so convenient, if I add these two equations together, the negative 4k and the positive 4k will cancel. 4j minus 8j makes negative 4j. And on the right side, the negative 16 minus 4 makes negative 20. And now I've got a nice simple equation to solve. If I divide both sides by negative 4, I get that j equals 5. And notice, if I wanted to, I could solve for k, but I don't need to get fancy here because all I want to do is find the side lengths for the rhombus. So it's perfectly fine if you want to take the time to solve for k. It's not a problem. I would choose the simplest equation here, j minus k equals negative 4. So if you really want to do this, you can. J minus k equals negative 4, but I know my value of j is 5. So I know 5 minus k equals negative 4. That's going to give me a value of k that's equal to 9. And that's fine, but I didn't really need to do that. All that I needed to do was find a side length. So once I know j is 5, notice I can plug that in. 2 times 5 makes 10. And 10 minus 4 is 6. I know that side length is 6. I know all of the side lengths are 6. Notice if I plug the j in here, 5 plus 1, again, that's 6. I didn't have to solve for the k, although I can confirm my answer. K is 9. 9 minus 3 is 6 again. Or up here, k is 9. 4 times 9 is 36. J is 5. 6 times 5 is 30. And 36 minus 30 is 6 once again, but I really didn't have to go to all of that work because once I knew what j was, I could find one of the sides. So this method is called elimination. Once you set up your two equations, you need to get the variables on one side and the constants on the other side, and then you want to eliminate one of the variables by making coefficients that are opposites. So I hope this has been a helpful reminder of how to do elimination. So I believe there's one question on your homework assignment that will involve elimination. We'll practice that a little bit more tomorrow. And I think we'll leave example 3 on the backside. I think we will leave that for tomorrow as well. Have a good day.